Um, Hello, everyone. I'm Hamidreza Malekian, PhD candidate at Zimmer University of Technology and affiliated PhD candidate at Archimanium. I've completed a year and a half of my 3 years PhD program under supervision of Dr. Gomaa and Dr. Latifi. I'm an architect and computational designer with a strong passion for bionic and digital design. Over the years, I've explored research in digital fabrication in both academia and industry. I'm particularly interested in integrating computational design with bionic approaches to tackle challenges in architecture and construction. So for my PhD, I proposed my research around two major issues in construction: the lack of sustainability and the need for it to evolve with new design methods. In fact, the construction sector is a major contributor to global waste and greenhouse gas emissions. By 2025, we're expecting that construction waste to hit 2.2 billion tons, with the market value reaching 232.1 billion US dollars. What's alarming is that around 30% of the material delivered to construction site end up as waste. Moreover, the construction industry is responsible for 34% of global energy-related CO2 emissions, and it accounts for 40% of annual greenhouse gas emissions. All these numbers show how urgently we need to change the thing in this field. Well, what is the gap? There are two key areas that impact the environment: the material used and the fabrication process. Many materials like concrete, steel, and plastic are non-biodegradable and hard to recycle. At the same time, the rise of computational tools in architecture has led to more design with complex geometries. But the thing is, the construction process, construction process hasn't kept the pace with these changes. For example, for fabricating architecture complex geometries, custom molds have been used, which is not very efficient and needs an upgrade. To address these issues, my research focuses on two main approaches: decarbonization by using renewable low-impact materials, and digitalization by leveraging tools and technologies for more efficient production. So how am I going to do that? When we talk about the material in construction, this study points out that earth still is a fantastic resource for construction. It has been used throughout history. It's a well-known material. It's abundant. It's readily available. It's low cost, and you can find it locally. So this makes it an ideal choice for construction in remote area. But the thing is, it still needs some work because it can crack and shrink, during fabrication. So we can fix it by adding additives like natural fibers. In fact, I'm looking into how combining earth with fibers, including hemp as a first option, mycelium as second, and spinifex as a third, can enhance strength, durability, and environmental benefits. Secondly, as I mentioned earlier, architects are really moving toward designing more complex geometries these days. A big innovation in this society is using adaptive mold system instead of custom molds. Unlike custom molds that can only be used once, this adjustable one can be modified for different configuration and designs. What am I going to do is using adaptive mold system along with a robotic arm for 3D printing to create large-scale freeform airspace by panels. So far, I've been taking some initial steps, like modifying the adaptive mold, redesigning the bed base mat, and designing a new nozzle. The thing is, I want high accuracy because I want to high accuracy from the adaptive mold because I want to 3D print on the adaptive mold. So I redesigned the existing chain bed mat into elastic rubber mat. I've also been working on a nozzle for 3D printing. The thing is, there are some challenges in air 3D printing, like clogging the nozzle or refilling the extruder or the tank. So I designed my own nozzle to tackle these challenges. Well, today, freeform concrete panels are quite popular. Like one of the building at my university, at Zimmer University, has them in its facade. But I think there is a gap, and I can fill it by using sustainable materials. and digital tools instead of traditional approaches. When it comes to final output of my research, there are a lot of projects out there looking into automation in earth construction. As I mentioned earlier, the main goal in my study is create complex shapes. So there are some projects that are using timber mold or metal mold. Some other looking for more intricate design or using a PETG printed mold. My research is in line with this effort, but instead of sticking to static molds, I'm going to use dynamic molds. So in the direction of my research, I have another goal. It's a future goal, actually, that I believe that make a difference in the industry, which is centered around the concept of from the site for the site. This means that by using soil from the site for construction and incorporating digital tools, we can save on cost and time, since we won't need to transport material to construction site. Plus, we can reduce the number of labor and increase the workload without sacrificing accuracy. And more importantly, on the top of all the benefits, this is a sustainable approach. However, achieving these goals involve confronting many challenges that I'm actually studying in a parallel with in the other research. To move forward, I've outlined several key steps. First, I'm going to finalize the design modification of the nozzle based on the feedback that I get from action. Then I'm going to focus on the material mixture by combining earth as a primary substance and hemp as an additive. Then I'm going to test the rubber mat. And after that, I'm going to 3D printing on the adaptive mold and fabricate a small scale prototype. This is for the next 6 months. And after that, I'm going to fabricate large scale prototypes. And at the end, I'm going to evaluate them. Thank you for listening. If you have any question or recommendation that help me or improve my research, I would love to hear it.
Thank you. Any questions, please? Yes, Claire, and then Azata.
Thanks, Hank. Thanks. That was a really great presentation to see. I feel similar comment earlier from a colleague over here around action research. It would be nice for you to be able to deploy that early on. I believe you're about 6 months into the PhD. So to be able to initiate a methodology now around how do you apply changes, particularly to the nozzle, and work in cross-disciplinary with industrial design teams, which we have a very strong team at Swinburne. So reach out for me if you need contact to them. I feel being able to put some actions now, do the research, evaluate that, then re-implement changes and continue to evolve. That's what true action research is. And for me, that's a perfect fit for your PhD.
Great presentation. Quite impressed. Could you explain? So you get. I'm new to this concept of from the side to the side. Is that right?
From the side for the side.
Yeah. So you're planning to get the soil from the side.
Yeah.
How do you know? I mean, could you elaborate a bit more? So it's quite costly actually get all that material and put into a pile. I mean, it's one of the most costly parts of the project, right? So could you elaborate on how you planning to do it? Are you going to reduce like a layer of the side? What is the method for that?
You've answered the question. Trying to see why.
So, as I mentioned earlier, we have a big problem here. So when we say we want to use the earth from the soil, soil from the soil, actually there are some projects out there that are looking for solving this issue. The issue is like when I say earth, it's not any earth. So we're looking for a kind of a specific ratio. So it's like, I don't know, 80% of soil and I don't know, 20%, 30% of clay. So if we want to use the earth from the site, we don't know if that earth is suitable for construction. So this is the problem. So and I say, I'm going to work on it to find a solution how we can use that earth for the construction. So yeah, this is a part of the research, and I hope I can get something that valuable, to use in the industry.
That would be amazing.
Yeah.
Great research.
Yeah.
Love what you do. Couple of questions. You talked about adaptive mold.
Yes.
Like, I wonder, like, how does this work? Like, because the mold was sitting on the metal bars that moves as the mold.
Yes.
But when you print on it with earth, like earth takes time to dry.
Yes.
So how would you, are you intending to leave the panel there for it to dry on the mold, or are you thinking of sort of a permanent form that you will print on top of it?
Okay. That's a good question. Okay. First of all, this is a great question, because I think this is kind of new. The adaptive mold, first of all, the adaptive mold is a grid of rods that work vertically that can create, freeform surfaces. So yes, we have to leave, the printed earth, by panels, for time, and then we have to bake it. Eventually we have to bake it because when it gets a little bit harder, then we bake it and we can use that.
Like adding fiber to it, like hemp and stuff, when you're baking it, those fibers. So like you might just as well just do ceramic panels.
Yeah.
Just well, thank you so much.
Yeah.
Great.
Yeah. It's a very interesting project, and I'm supervising somebody actually who's author of one of your projects in Barcelona.
Yeah.
Why are you interested in freeform, adaptable molding?
First thing, I think there is a huge interest, in using parametric tools in designing different shapes, and I thought this is the gap that we cannot create those shapes with a mold that can be modified and configured in different designs. So it's like most of all they're using the custom molds. The custom molds, it's not reusable. So it's reusable, but it's like you have to use it just once, and if you want to use it again, you have to create another custom mold. So I thought this is the opportunity that I can use the adaptive mold for fabricating.
See, a lot of the freeform has come from a time when we thought that was a reasonable way to approach high architecture.
Okay.
But now that we're sort of more focusing on the real cost of building on the environment,
Mhm.
It seems to me that the idea of an adaptive mold for the shape of bricks, for instance, would be a more reasonable challenge than having an aesthetic agenda. Because if the free form is actually around performance, like you've got a theory around a better performing building if you have free form surfaces. I'm just wondering if that's a challenge you really need. If that isn't your motivation, then the adaptive molding, I would have thought, would be around the shape of components that stack together like bricks, because that's going to be a challenge enough. And the idea that you can have a mold that you're not stuck to a modular size, I would have thought that that's challenge enough. But we can just
I think cost, time, and sustainable. These are all aspects that motivate me to use adaptive mold.
Hi, thanks. Super interesting presentation. Can I just clarify? You're going to use soil with hemp, and
Yes.
then you're going to bake it.
No. I'm going to 3D print it, and then I'm going to leave it for a time till it gets harder, and then I'm going to bake it.
When you say bake it, are you putting it in a kiln, or what temperature are you firing or baking it to?
So I'm not.
If it's to be vitrified enough to be able to withstand water, are you looking at like 1,000 degrees or?
I don't think so. As I said, because I'm just I just completed a year and a half. So this is part of my methodology, and next year, so we didn't set, you know, the temperature that I'm going to bake it. There are some limitation because we want to, you know, to use different fibers. You know, we have hemp, we have mycelium, we have the spinifex. And each one of those, you know, we need set different temperature for baking them. So
I'd be happy to talk with you about it. I've got an undergrad in ceramics, so firing and temperature and baking is something that can maybe help with, because the fibers will burn out at different temperatures,
Yes.
which then create a porosity in the forms, and that's something that you either may want to use for structural strength, or you may want to not have it burn out, which means your baking temperature for vitrification could only go up to like 180. So anyway, happy to chat about it later.
Okay.
Thanks, great presentation.
Are there any other questions? No, wonderful. Then thank you for your presentation. And we will move on